Hello guys, in this video I'm going to talk about the Gaussian mixture model. So in the previous lecture we saw the k-means clustering and note that in k-means clustering we just fitted circles. So here you can see we have just estimated means, hence the name is k-means. We have to just estimate the means. So we are allotting pixels, assignment, estimating mean, that's it. So it would be better if we would also calculate the variances. So if suppose we take variances also into consideration and basically fit a Gaussian curve over this, then we get a Gaussian mixture model. So let me visualize this in a one dimensional feature vector or one dimensional data. So let us say suppose I have some likelihood of sunflower. So here this is from my images. So here these are the images of sunflower. I am just plotting the size of the sunflower of every image. So the first image size maybe say some value over here, the second image size over here. So I am plotting the size of my different training data on the x-axis, and I am seeing that here there is a lot of samples that are put over. So basically there are a lot of samples over here, there are quite a few over here, and quite a few over here. So if in case I want to model a probability density function, then it would be something like this. So this is the probability axis. I'm calculating the probability that given it is sunflower, it will have some size. So this is that size that we'll have. So you can see that there is no sample on 0. You cannot have 0 size, right? So the probability might start from here. You can see there are quite a few samples over here. So the probability of getting a new sample, a test sample in this range, could be somewhat like this. It is high. So here getting probability is somewhat high. Next you can see that this probability is even higher. Here there are many samples, so here the probability is even higher. And as and when you go here, the probability is very low, so hence you are going down. And then here you can see it is okay, it is not very high, it is not, it is okay. So I'll go like this, and here it is again low. So this is a sort of a probability density function that you can estimate from the data that I have, the training data that I have, right? So here you can see what essentially we were doing was just trying to fit one Gaussian over this. So we were till now trying to fit only one Gaussian over this, which is not the best method, right? Here you can see that there is this region where the probability is very less. Again, there is this region where the probability is very less, and there are some modes where a local maxima kind of thing. So here you have the probability is high. So instead of just fitting one Gaussian, what if we fit three Gaussians? So let this be one of my Gaussians. So this is my first Gaussian that I am going to fit. This is going to be my next Gaussian, and this is going to be my third Gaussian. So you can see if suppose I fit three Gaussians, it gives me a quite better approximate than what I was doing earlier. I was just fitting one Gaussian like this, which is not the best way, right? So this is what we do in Gaussian mixture model. We fit many Gaussians for the same class. So here please note that I am not changing my class. My class is still sunflower. This is the likelihood of the sunflower only, and here I am going to fit 3 or more than 3 or any k number of Gaussians. That is what I am going to do. So this is very similar to the k-means. In fact, k-means is just a special case of the Gaussian mixture model, where in k-means what we do is we just find the mean, and we basically ignore the variance. We just see which is closer to which, and you take that. You just ignore the variance. And in Gaussian, what we are going to do is we are going to take the mean, the variance, and then plot the circles or ellipse. So in Gaussian, there is a good chance that you get ellipses, and that will be a further better approximation of the PDF that you want. So the PDF of likelihood. So this is all that we are talking is on for the likelihood. So given that I have some class, given that I have some training samples, what is the probability that will have this feature vector x? That is what we are finding, the likelihood, right? So mathematically I can denote this likelihood like this. So it is some p of x. Okay, here please note that I am changing the notations now, because for the whole lecture we are just going to talk about one class. Here there is no rose or some other flower that is going to come. So I am, because I am going to have some other notations also. So I am writing this p of x given sunflower as p of x. So because it is given that I am only dealing with the sunflower data, so I remove that given thing because it is explicit that I am using only sunflower data. Yeah, I am doing using only one particular class. So hence I am removing this notation, because further there will be things that are going to be a little congested if I use sunflower everywhere. So that is the only reason. So I am denoting this as p of x, and you can see that this p of x is nothing but it is a summation of different Gaussians. So here say this Gaussian will have a mean mu1, say this Gaussian will have a mean mu2, and this will have a mean mu3. Also this will have some variance sigma 1, some variance sigma 2. Okay, let me denote this as like this, and some variance as sigma. Okay, I made this one, so let this be 1, this is 2, and this is 3, right? So this is what we'll have. So this is for a one dimensional case where I am getting just means and variances, pure variances. But then if you elaborate this to a two dimensional case, what you'll get is a covariance matrix. So also you can see that these peaks are different, like this is higher, this is smaller, this is smaller, even smaller. So there are some weights that are multiplied. The Gaussians are not directly added. The Gaussians are first multiplied with some weights, and then we have adding them up. So also please remember that the area under PDF should be 1. So even if I am adding these Gaussians, I cannot add Gaussians directly. So this, because a Gaussian will have an area 1, and when I add this with another Gaussian, this will also have an area 1, which will make the area 2, which is wrong. PDF cannot have area greater than 1, right? So hence we'll have to multiply this by some factor which is in between 0 and 1, and also this with some factor which is between 0 and 1, and then you can make the area addition as 1. So you can multiply this by 0.7, this by zero point 0.3, and this will become 0.7, this will become 0.3, and the area will become 1. So you can also say that pi k is the probability that a sample falls in a given Gaussian. So the probability that a sample will fall in this Gaussian, the prior probability. So suppose you don't have the sample data, you are just having these three Gaussians. So what is the probability that a sample will fall in any of the three? So it is 1 by 3. But because of these things that you see, because this is a little high here, it is more probable that it will fall. So there will be some other value, say there will be some say 5 by 8, something like that. So 5 by 8 could be the probability for this. So, and suppose 2 by 8 could be the probability for this, and 1 by 8 could be the probability for this. So because here there are more samples, right, this is more probable, so I'm giving a bigger weight to this. So this essentially will sum up to 1. So these things are nothing but my pi k's, so that is a weight added. So also by this you can get this insight that pi k will always fall in between 0 and 1, because to make my PDF less than 1, the whole PDF should be less than 1. So if I make this only 2 or 3, that will increase the PDF, which is wrong. Also, summation of all these pi k's should be 1. So 2 by 8, 5 by 8 plus 5 by 8, that makes 7 by 8, plus 1 by 8, that makes 8 by 8. So this should also be 1. So this just uh, gives you the notion that the PDF should have the area 1. That's it. Right. So let me first tell you what do we want to do. So now the problem is we just have the data. The same problem that was with the k-means clustering, that we just have the data. So this data again, if you see, it is in form of a vector matrix. So the first data will have this coordinate, this coordinate, this one. So for the 1D data there will be just numbers, like vector numbers. So say this thing is 0.1 or some 3 or 4 or 6 or 7, something like that. So these are all vector numbers. So it is very difficult to find out which number will lie under which Gaussian. So what I want to calculate is, given some feature vector. So I'll do some sort of training, and after that in the testing phase, say I have some image of sunflower which has test vector say 5. So which has test vector say 5. So given some test vector 5, what is the probability that it lies in one of these Gaussians? What is the probability that it lies, say, in Gaussian 1? So that is what I have to find out. What is the probability that given some feature vector from the training set, what is the probability? I'll tell you what variable will come over here, but please see the intuition behind it, that I am given with some test vector. Now I have done with training. So I'm first telling you the problem, what do we have to go, and then I'll show you the path. So this is our destination, that given some sample, first I'll have to classify whether it comes into which Gaussian, because now there is not only one Gaussian but there are three. So there is this thing that we have to find out. Okay, so what I'm going to do is I'm going to denote every Gaussian with one variable. So I'm saying that this Gaussian is variable z1, this Gaussian is variable z2, and this Gaussian is variable z3. So what am I saying is that if x is equal to 5 is a given test sample, so I am given with a test sample whose size is 5. So what is the probability that it falls under some zk, where k can be 1, k can be 2, k can be 3. So what is the probability that it falls under some zk, given that my test sample is having some value, say 5. So here there is this concept of latent variables. I have just introduced this zk so that I can differentiate between the Gaussians. I can say if it is 1, so it belongs to this Gaussian. If the probability of 1 is higher, then it will belong to this Gaussian. If the probability of 2 is higher, it will belong to this Gaussian, and 3 is higher, then it will belong to this Gaussian. So hence I am using a variable, so which is a little sort of hidden. So this variable we did not have anywhere, but I am introducing this to make things easy. So here zk is just telling you, pointing which Gaussian will it go basically. Right. So also please see that these will be binary. So if suppose z1 is 1, that means that this will go to this particular what we say, a Gaussian. This test sample will be allotted to this Gaussian. If z1 is 0, that means that it will not get allotted to this Gaussian, it will be something else. So for this sample, say z1 will be 1 and z2 will be 0 and z3 will also be 0, so it is not getting allotted to this. Also you can see that since I had these prior probabilities which were my pi k, so you can see the probability of z1 becoming 1. So that is the probability that the sample will go in this particular curve. The prior probability is nothing but pi k, because what is the probability that a particular sample will go in this Gaussian when you have no information. It is just the prior that you have, so that is pi k. So from this we get p of zk is equal to 1 is nothing but pi k. So p of z1 is equal to 1 will be pi 1, so that will be say some 2 by 8, this will be some 5 by 8, and this will be some what we say, 1 by 8, right? So moving further, now it is just pure mathematics that we have to see. So this I have defined as p of z. So this is some prior probability, that is nothing but our pi k. So now I have just changed the notation of pi k to this, because this will make things simpler hereafter. So p of x given zk is equal to 1. Now it is given that the particular sample belongs to this particular, what we say, Gaussian. Now what is the probability that it will have a particular size? So given this Gaussian, what size do you expect that these will have? So that is nothing but the formula of the Gaussian. So if suppose I have just been given with this Gaussian, now tell me what is the probability that a particular given sunflower, a particular x will fall over here. So that is given by the formula of the Gaussian. So they will be normally distributed along x given with mean mu1 in this case, and covariance or variance sigma 1 square. So this is important. So this is what, this is when I'm given that so this was the first thing, what is the probability that this can be the case, this can be the case, or this can be the case. Then I'm saying, okay, now it is given that it is this case, chalo, now tell me what is the probability that so this can be thought of somewhat as likelihood, but we'll not term it as likelihood, because this is the main likelihood that we have, right? So this is so for mu1 you will have a mu1 and a sigma 1. So this denotes that I'm telling about this Gaussian. Now the total probability of x, p of x, which I had also shown over here, I'm just substituting my latent variables into this probability. So here you can see that my pi k I can denote as this p of z zk. So p of zk is equal to 1 is my pi k. So I have written, instead of pi k, p of zk is equal to 1. That is the whole thing. Also this particular Gaussian over here, this I can write it as p of x given zk is equal to some 1. So now I'm given with, say, zk is this, or say zk is this. Now tell me the probability of the size. So that you can see, so you can just relate these both are same, so that comes over here, and pi k is this. So now by this we just converted our expression from these values to some latent values, that is z. Now please remember what did I have to find? I have to find this. I am given with some feature vector. I am given this test image. I am given with some feature vector x is equal to 5, suppose. I have to find out the probability that it falls into some of the Gaussian. That is what I have to find out. So here this is not the case. It is this that I have to find out. So it is something opposite. I have been given this and I have to find zk. So again the Bayes rule comes to our rescue, and from the Bayes rule we can write this. So p of zk given is equal to 1 given x is nothing but p of x given zk into p of zk upon p of x. So please concentrate and please try to understand what is this. This is what is our important thing. This will essentially assign a particular x to a particular Gaussian. That is what we want over here. Okay, next so this is also a big notation, and since this is a very important thing, I am going to change this. So I am just writing this as some r of zk. This is actually r of znk. So this is r of znk. So for a particular sample, so I will have some sample. So the first sample, second sample, third sample, fourth sample, so that is denoted by this n. And because of this I will have to put a n over here. So that says first sample, second sample, third sample. And k tells you which Gaussian will it belong to. So will it belong to the first, the second, or the third Gaussian? That's important. So here I have just now this I have written as pi k. So this is the same. And p of x is nothing but this. So it is this also. So I have written this over here. So now that I have got this particular thing, I am just using where I want to use the zk, and others I am converting back to the formula. Okay, so now here this is being calculated for one particular sample of x. If suppose I assume that all the samples are independent, so again let us see what is independent. So independence basically means that the first image is having a feature vector, say feature 6, the what we say, the size 6. That does not give you any information that the second would also have 6 or 7 or 8. That does not give you any information. So that is when I say the samples are independent. Right. So the total p of x, the total for everything, will be nothing but the product of all the samples probabilities. So this we have seen so many times in the course. And for the same reason, now there can be a sample over here for which this Gaussian will make it tend to 0. So the product will again tend to 0. So this is the same case that we see in maximum likelihood and such sort of parameter estimation problems. So we take the log. So we take the log, and this takes so this solves the problem of getting a 0 here. Right. So here I had my p of xi. So what is p of xi? P of xi is nothing but this, p of xi. And remember, I have to maximize this. I have to maximize my likelihood. So because I have to find the parameters mu k, sigma k, and pi k. I don't know these parameters yet, because I don't know what will be the mean of the first Gaussian, what will be the mean of the second Gaussian, the mean of the third Gaussian, the variance of the first Gaussian, second and third Gaussian. So that is unknown to me. So how I find that? So I'll find that by maximizing this probability. So I just want to maximize the probability over here. So that is the same thing that we used to do in maximum likelihood problems. So I have to maximize this probability given the parameters mu k, sigma k, and pi k. So we'll see in the next lecture how do I calculate the parameters mu k, sigma k, and pi k. So this is also one sort of maximum likelihood method, because this is the likelihood now that is given to me. Initially it was just one Gaussian. When I first uploaded my video on maximum likelihood, it was just one Gaussian, and I just had to calculate one mean and one variance or covariance. But now there are three means, or in general k means and k covariances and k pi k's. So I'll have to calculate all of these. So we'll see how do we do